Yeah, thanks everyone. So I think I'll get straight into it. So I'm talking about OpenCL, saving parallel programmers pain today. So a quick recap. So we all know that parallel programming is of increasing importance in an era of multi-core devices where cores aren't getting faster, but they're adding more of them. So hardware engineers have left us a bit of work to do. So as the trend is to add more cores, and typical CPUs contain, 1 to 12 high-frequency cores. But each vendor tries to push their own specific language to target these platforms. So Intel promotes Cilk Plus, or thread building blocks. Thankfully, they also support OpenMP and OpenCL. GPUs have thousands of low-frequency cores, and NVIDIA promotes CUDA. Thankfully, AMD mostly uses OpenCL as well. And integrated systems on a chip with accelerator devices. So Texas Instruments have a Keystone 2, which is an ARM A15 quad-core processor with 8 DSPs on the same system on chip. And they're pretty cool, but their main line of development at the moment, they use Texas code generation tools and DSP compiler, CL6X. So it's not easy to successfully run code on many cores. So what is OpenCL? So OpenCL isn't the Java of high-performance computing. OpenCL is, or Open Compute Language, is an open standard which defines a common C API. So it's pretty low level. OpenCL, to quote Kronos Group, is the first open, royalty-free standard for cross-platform parallel programming of modern processors found in personal computers, servers, and handheld embedded devices. So if C or C++ isn't to your liking, there are a variety of wrappers around the API for other language support, including Python, Lisp, Java, Pascal, Erlang, Go, Rust, Node.js, Lua, all the languages. You could write your own bindings to OpenCL. So the main idea and the benefit to doing something in OpenCL, it's not the easiest language to get started in. But once you have it going, you can write once, and if you do a good job of it, you can run it pretty well on CPUs, DSPs, GPUs, FPGAs, and any type of amalgamation with the system on chips we're seeing now. Okay, so OpenCL is a pretty mature language. It's not a spring chicken anymore, and they tend to add or revise the spec every year or two, and it's well supported across most vendors that produce anything with a processor. Okay, so I'll try to motivate this a little bit. So over the past 9 months, I've migrated some ultrasound simulation code from OpenMP to CUDA. And we used CUDA initially because we're interested in using some of their CUDA FFT, so their fast Fourier transform library, and their cuBLAS basic linear algebra subprograms library. But unfortunately, once we moved into using CUDA, we're locked into NVIDIA's ecosystem, which is fine at the moment. They have some interesting, they have some of the best performing hardware for our particular applications. But what happens, 2 years down the track when the next vendor produces something cool? I don't want to. So I mean, when we're locked into a specific vendor, it fragments the software development industry. I don't want to have to rewrite all my code for another target platform 2 years down the track. So think of the children. It's bad enough I have to migrate my code to another vendor and moved into their lockdown ecosystem, but it's unacceptable to leave it for someone else. Okay. So I'll try to. So there's a plan. So don't worry, there is a plan. Throughout this talk, I will discuss a simple application that will benefit from parallel execution and the process of tuning serial code. From there, I'll prototype parallelism with OpenMP, and then move from that prototype to production OpenCL code. And I'll show you how you can write your kernels pretty well once, and it'll run on a variety of interesting platforms. Okay, so I'll motivate it. So the application's a continuous wavelet transform, and it's useful for signal analysis, speech recognition, earthquake detection, bird and whale audio signal classification, deep sea exploration, and music restoration. So it's useful for a variety of fields, but unfortunately it is order n cubed, and larger sizes generally give us the most interesting applications. But thankfully, parallelism can help stave off this polynomial growth in computation. So this is what the CWT does. So this is only in a one-dimensional signal. We feed in a one-dimensional signal, and we're generating a continuous wavelet transform, which is 2 dimensions. We get an additional redundancy, but it's over, so we get scale and translation. So it's really good at visualization. And this is computed by, so we have the mother wavelet on the left. In this case, it's a Mexican hat. It looks like a hat. And on the right is our input signal. And at for each point in that grid you saw, we want to generate, we want to store the result of, we want to generate a daughter wavelet, which is that mother wavelet sort of squashed or scaled to a different size and shifted across the signal. So we scale, and then we move it through the signal. And once we get to each point, we would do like a filtering operation, where we multiply each coefficient together and sum the result. And then we'd store that result so that for that unique scale and translation. Okay, so the prototype, so the computational kernel was initially written in R, and then I tried to make this as C-like as possible, even though R is terrible at doing iteration. They even say in their documentation, do not use iterative methods in R. So then I mapped it to C++. So this is the R code. Can everyone see that okay? I tried to make it as big as possible. So the Mexican hat function in the top. So the most important portion is there's 3 nested for loops. So for the outer for loop, there's A is scale, the middle for loop is B is translation, and the inner for loop is I, which is the convolution, which iterates across the whole signal and does pointwise multiplication and a sum. Okay, and then so that maps pretty well to C++. So there's only a little bit of tuning. I mean, the function's inlined because it's called at each iteration. That's quite expensive. And we just move some computationally expensive portions out of the inner loops. So this is as bare bones as you can get it. Okay. So R versus C++. So R is terrible at iteration, as I said before. So for 2 to the power 7 elements long, R takes 18 seconds, or 18.3 seconds, and C++ takes 40 milliseconds, which is roughly 458 times faster, but why stop at that? Because, I mean, even with one thread or one core on, in C++, this still takes about a week to compute. So maybe we can help alleviate this with some parallelism. Okay, so so CPU's granularity of parallelism. So CPUs have fewer general purpose cores, and so we want to have, since we have fewer cores, we want them to do as much work as possible, and we evenly divide it. So we want to have heavyweight cores that do heavyweight threads that do lots of work, and fewer threads because we don't want to do context switching. So we have our scale and translation. Thread 1 will operate on the first scale, and it'll go away and do its own business and do a convolution at each translation, like so. We also have, we have 4 threads in this processor. So we have, thread 1's on scale 1, thread 2 on scale 2, and so on. And what happens if thread 1 finishes earlier? It's going to stride. So that's the behavior we want, and so that's the coarsest granularity of parallelism we can use. It's either that or we do the exact same thing with translation, but because that's in the middle loop of that for loop, that it imposes a barrier at every step for every scale. Okay, so we can prototype parallelism pretty easily with OpenMP. So OpenMP offers programmers a simple and flexible interface to parallelize code. It offers a runtime API, so we can call like OMP set num threads, and we can set the number of threads we want to use using the runtime API. So we can change how many CPUs are in use, and directives. So we can use OpenMP pragmas if your compiler supports them. which is great because you can turn it off and see if your serial code works, because I'm notoriously bad at breaking my code when I try to make it run in parallel. Okay, so this is even harder to see. But basically, it's the exact same region I showed you before, but with the Pragma OMP parallel 4 on the top. Okay, and I don't like what OpenMP does behind the scenes. So I explicitly say this is all shared memory. And you generally have to be careful when you use shared memory on writes, because only CWT data is written, but it has a unique identifier for each thread in A. Schedule static is basically the one scale each, and it'll stride. Okay. So this is over 128 points long. So our signal's 128 points long, and this is on a Xeon X5650. It has 6 physical cores and 6 hyper-threaded cores, and it's not surprising we see the sweet spot is about 12 threads. So 12 OpenMP threads maps to 12 cores on this Intel processor. So it's not about 9 times faster. But does it scale for bigger data sizes? Because we really want to get up to 2 to the 13 sort of ballpark, and not really. It can do 1,024 grid points pretty quick. But what about using different hardware? We can try to make this faster using different hardware. So enter OpenCL. So we can write once and run anywhere with OpenCL. Unfortunately, at the moment, the lowest common denominator between all the target platforms I'm looking at is they're running OpenCL version 1.1, which still uses the relatively low-level C API. So I'll get into a little bit of the nitty-gritty. I'm not going to show you lots of OpenCL code, because thankfully that's copy and paste, and it's pretty much the same for all projects. But the principal component is there's two programs you have to actually write to get your OpenCL code running. So there's a host and device side. So the host side has a platform layer and a runtime layer. And the platform layer is responsible for querying the platform and querying the device and establishing a command queue. So I mean, different platforms would be if I have NVIDIA cards on my system, and I also have an Intel processor. And then you specifically say which card you want to use. And then the host has to deal with runtime operations, like it creates memory buffers and compiles the kernel, sets the arguments, and executes it. But like I said, fear not. Most of this is copy and paste between projects. So you can feel free to use my code as a starting point if you want, or any other on GitHub. So the kernel on the device. So the kernel's the other program that's actually being run on these accelerated devices, and it's a little bit more interesting. So the kernel code is a restricted subset of C. The __ kernel qualifier declares a function that can be executed on the device. And the __ global address space is memory that's mapped directly on the device. So the host would create global memory, and the kernel can use it, and it's explicit. So we can call functions from the kernel, and general math functions are supported. So you can see I can still inline my Mexican hat function, and I pass anything that's array. All these are stored globally on the device. So these are vectors, and this is basically a matrix, the output value. And so this is the computational region. Again, this is all exactly the same for the for loops. But the only thing that I'd really suggest is OpenCL kernel compilation also supports preprocessor directives. So you can target the granularity of parallelism once. So if you do a good job at writing your kernel once, you can just change these flags from the host side code without ever revising it, because revising these kernels, it takes a bit of work to figure out what's going on. You really only want to do it once. So there's a couple of runtime calls that the device can use on the kernel. So you can get global ID, and followed by a numerical argument, and the numerical argument specifies the dimension of the computation. So 0 in this case would be the x or scale dimension, and 1 is the translation dimension. Okay, and also get global size with the dimensional argument specifies how many threads or how many work items are supposed to be running in this work group. So this works well in our CPU code because we can work out, okay, from that example, there's 4 threads in get global size 0 that would return 4, and we're striding by 4 every time. Okay, so targeting and tuning on the host. So there's only, once you get all the boilerplate OpenCL stuff down, it really only comes down to about 3 lines of code you have to change to run on all these devices. So to assess the efficiency of the OpenCL implementation, let's first start and compare against the OpenMP on the same processor. So running the code on a CPU is done by specifying the target. So when we go CL get device IDs, we're only changing CL device type CPU. So we're targeting what device we're interested in. Next, we specify the granularity of parallelism with those OpenMP with the directives flag. Sorry. So we change our compilation flags by commenting out the inner loop. So instead of striding over the parallel region, and so local work size is more for threads that work together in a team, and that's really useful on GPUs, but not so much on CPUs. We sort of leave them all to themselves. So that's a 3-dimensional region. So so the local work size is basically just yourself, just one thread to itself. And across the total computation, there's 12 threads in the X dimension, and one and one across the Y and Z. And I don't use Z yet. Okay, so comparing OpenMP to OpenCL, so for the wall clock times, so we can see OpenCL is a little bit faster, but that could just be an unfair comparison. It's marginal, and there's an OpenMP scheduler that has to kick in for that static striding. So it goes from 9 times faster to 10 times faster with OpenCL. But since we know our OpenCL implementation is correct, because we can prototype on these CPU cards, on the CPU, we can then just target different devices, accelerators, and so on. So how does it do over different lengths of data? So from now on, I'll just go over different sizes of n for our input vector. So we'll first go with CPUs. So I have an i7 2820QM, and that has four physical cores and 4 hyper-threaded cores. So all the tuning that has to occur is, since we have eight global work items and they're CPUs, so they don't play well together, we leave it 111 in the local workgroup size and 811 in the global workgroup size. And again, we still want just this outer level scale loop parallelism. And the same for the X5650, except it has six physical cores and 6 hyper-threaded cores, so we change the global work size to 12. And this is how it performs. So profiling indicates this is a memory-bound problem. So we're waiting on a lot of reads, loads and stores, because we don't have regular memory access in that kernel. So GPUs are really good at hiding memory, global memory accesses, because context switching is really cheap on a GPU. So you fix it because you can have lots and lots of threads running. On NVIDIA, it's called a warp, or on AMD, it's called a wavefront. Basically, there's 64 or 32 threads that can be executed at one time on these processors. And as long as you have a local workgroup size that's bigger than that, it has to be a multiple of 16, but say you had 128, so 32 are going to be executed at once. So those 32 threads can go do their operations. They hit a load. They're going to wait around for a few cycles. Then the runtime will put them to sleep, and then another 16 will go, another 32 will go, and so on. So GPU granularity of parallelism. So since we only have a small number of small length of the input data, and GPUs have thousands of these lightweight threads, they should only do a small portion of the work. More threads means more context switching, which is cheap on GPUs. So on a GPU, we have this ND range. I mean, it's the same on the CPU, but we don't really need it so much. And they all have their own work groups, and they have their own localized work items within a work group. So the work groups are mostly used if you have local shared memory between threads. So threads in that team or that work group. But I only use global memory accesses, so I can just query wherever I am in the ND range. So now I want to throw at each grid point a thread in whatever teams works out to be optimal, and that's just flag passing, and then see how it scales. So to target a GPU on OpenCL, I change that was CL device type CPU. It's now CL device type GPU. I uncomment this line of code, and now it's parallelizing along both loops and striding along both loops. So if we still had, so if the GPU only has a maximum number of cores, we might only set that, and it'll stride still. And we build the kernel and execute it. So I have 3 different GPUs to compare it against. I have the ATI Radeon HD 6750M, which is in my MacBook, and that. So this is all fun and games. So the global work size I just set as data length, so that could be n. So if our input, that's as big as our input signal is basically. So it's total amount of work that needs to be done. And then however these warps are scheduled, I'm doing it on the translation loop, so that in a loop, the middle loop rather. So that's why and there's 128. So 128 threads work together to get the job done. So if one team is waiting on a load, it'll schedule another team and so on. Then I compare it on a GTX 580. So the only difference is I have 256 threads in a local workgroup size, and a Tesla K20 with the same configuration as the same tuning flags as the GeForce 580. And this is how well it performs. So it's pretty interesting because both the Tesla card and the GeForce card can compute 2 to the power of 13 grid points pretty quickly. The Tesla can do it in about 13 seconds. And it's not surprising. I mean, this Radeon card is a mobile processor, and it's only operating at 150 megahertz compared to 1.5 gigahertz of the gaming card, the Tesla gaming card, and 705 megahertz of the Tesla card, but it has twice as many cores. So what about accelerators? So OpenCL can also coordinate accelerator devices just as easily. And these include the Intel Xeon Phi, or the 7110P, which has 60 quad-core Pentium cores. That's 240 work cores. It's running at 300 watts. And we can compare this against a Texas Instruments Keystone 2 system on chip. That's with the ARM A15 processor and 8 DSPs. And that entire system on a chip is operating at 15 watts. So to tune it in OpenCL, CL device type accelerator now, and that's pretty much all you have to do. And because we have, so even on the Phi, so for the Keystone 2 has 8 DSPs, and each DSP is treated as a thread. So we only set that to 8. But we only really need the outer loop parallelism. Okay, so here's the configuration for the Phi. So it has 240 individual cores. So we feed it 240 threads in the x-axis along the scale. And the Keystone 2 with 8, because it only has 8 DSPs. And this is how it performs. So the Xeon Phi it's pretty quick. I mean, and to do the additional 2 grid points, it can do twice as many grid points before it tanks. But I think it's pretty interesting considering there's an additional 285 watts that goes into those additional grid points. And there's the comparison on all platforms. So again, the Tesla K20 is the best performing device, but for any of the benchmarks I've seen, the Tesla's been outperforming the Phi lately. And this is just on a log scale. So in the future, OpenMP 4.0 released accelerator directives, and that should map parallel regions to execution on these auxiliary devices. So you can do, instead of doing the hashtag pragma OMP parallel 4, you can do hashtag pragma OMP parallel accelerator. And that should map to something that would run automatically on the device. In reality, that'll probably leverage OpenCL to do this. And I think that high level abstraction would be sufficient because OpenMP gets away with that granularity of parallelism. But it's not there yet. I think we have to wait a few more years before it'll be supported. In the meantime, I think it's great that all these vendors support this open specification, and it's a minimal amount of work to get these devices running. It's like 3 lines of code had to be changed to get this code running on these variety of devices. So I think we should all get behind OpenCL because it's saving us from the software development industry is really fragmented by all these proprietary APIs, and you could train monkeys to map code to a different language. And I think the only reason why CUDA is pretty prevalent is the use of pre-rolled libraries like BLAS and FFTs. So we should really try to have an implementation that OpenCL can use. And also, the latest spec of OpenCL came out 2 months ago, version 2.0. So it allows pipes, dynamic parallelism, shared virtual memory, atomic functions, read-write, image objects. And so the more people, so lately, NVIDIA seem to be pulling support from OpenCL. They seem to stop at version 1.1, and it's been quite a few. It's been 2 years since 1.2 came out, and they seem to be really pushing CUDA out of their own interests. It'd be nice if more people could get on the OpenCL bandwagon, and then they'll be forced into supporting the latest version of the standard. And 2.0 provides a nice C++ wrapper API, instead of writing 40 lines of that boilerplate OpenCL code. It's just pretty much 2 lines, two lines to coordinate. Yeah. Take-home notes. OpenCL is a powerful tool, but don't go charging in. Tools like OpenMP are great at rapidly prototyping different granularities of parallelism, and you should prototype and profile often. Also, a scalable parallel program starts out as an efficient serial one. And so thank you to NVIDIA for donating some of the Tesla cards, and Texas Instruments for the OpenCL runtime for the Keystone 2, and CSIRO for access to the Xeon Phi. Thanks.
There's plenty of time for questions.
More of an observation. You've done all this with the binary drivers, I assume. AMD have been working on an open source OpenCL driver for the last while.
Yep.
But they have real problems finding anything to run on it. There's just like they're putting this chicken and egg situation. Like we've got an LLVM based compiler that can do OpenCL, but we have no idea if actually, we have all the main thing they run on it is Bitcoin mining.
Yeah. That's what AMD cards have been pitched for lately.
Please repeat the question if you can.
Do you know if there's like more, any way to put sort of code out there for people to actually use around it? Test sort of code and test shaders, and that code you've written, is that available on a license they can use? That sort of thing.
So there's a lack of available OpenCL test code to be run.
Okay, OpenCL applications or OpenCL source that they can use.
Yeah.
Actually test it.
Yeah. So I'm going to push this out on GitHub soon. I'll push it out once I finish the. I'll add one with the flag when I push it out on GitHub. But I think there's a significant problem in that OpenCL's been around for 5 years, and there aren't many applications that are written in it. It's a pretty low level, complicated kettle of fish. But yeah, there definitely should be more applications written in it. Yeah.
I believe you said at the start of your talk you're a PhD student.
Yes.
I want to make the observation that you also said it's going to take a long time for GCC Phi to start to implement some of this stuff. There are many PhD theses that have ended up abandoned because the author started contributing to open source work. And I'm just saying this might be your future.
Okay.
GCC.
Yeah.
Is it safe to run untrusted OpenCL code? So like if you provide a GPU for VMs to run, is it safe to let them run OpenCL code on GPU?
Is OpenCL, so the question was, is OpenCL safe to run, is it safe to run untrusted? Sort of. The worst I've been able to do maliciously on myself is not release control of my device context or use up the whole memory buffer so I can't get read rules on the screen. I suppose it makes sense. You can access yes. So if they map, so I mean you'd be able to see on the host if you mean by malicious, because you have to set up global memory between the card and the host. You could see on the host side whether it's staging anything to the card. But if you mean just like bring down your system, you can kill your terminal pretty quick. I mean, you can kill your display pretty quick.
More of us, it seems like an interesting business opportunity is to offer computing power to VM customers. But that obviously you'd have to work with the API and make sure it develops in that direction.
Yeah. You can Amazon Web Services. They share. I mean, you can get GPU resources there, can't you?
Yeah, they've got CUDA. I'm not sure.
Yes.
So in CUDA, you have to, particularly when you've got less threads available than you have cores to run it on.
Yep.
You spend a lot of effort tuning the memory accesses to make efficient use of memory location and fetch.
Yep.
Does that still apply in OpenCL, or does that distract that somewhat?
No, absolutely. So do you still have to worry about memory accesses like you do in CUDA on OpenCL? Absolutely. Everything you do in CUDA is more low level than OpenCL. Everything's more explicit. But I mean, I didn't deal with contiguous blocking of memory either. But yes, it's not automated in OpenCL. Yep.
How well do you find OpenCL applies to problems where you're crunching a large data stream? My interest, for example, is parallelizing large database aggregate queries.
Okay. So I have a terrible memory.
Stream of incoming
yeah.
data rather than looping over a small amount of data.
Yeah.
How well does OpenCL on GPU handle that?
Just
Thinking, for example, about a large statistical aggregate.
yeah. So you can absolutely use GPUs to process streams of data, and I imagine it works just as well as you would with CUDA. And you can set up a stream and keep feeding values into the stream. But I haven't dealt much with streaming data on GPUs. So. Anyone else? Yep.
This is more aimed at people who don't remember this, but I was curious as to why OpenCL is for Linux GPUs, for Intel GPUs is available for Windows but not Linux.
That is an interesting observation. That
There's an open source project for Intel GPUs that does have OpenCL support. There's OpenCL for Intel GPUs called Benyon.
Well, it's pretty great.
Trying to fix that.
Basically, instead of using LLVM natively for the instruction set, it produces NVIDIA's instruction set.
It's all kinds of crazy. I'm trying to fix that. That's a political problem, not a technical problem.
Okay.
Cool. Thank you.
Thanks, guys.
Thank you very much, folks.